Hello everyone. Today I'll be considering the operation principles of aircrafts. The operation principles guiding aircrafts. The operation of an aircraft involves multiple principles of physics and engineering. It combines multiple principles from physics and engineering together. The number one principle that I'm going to consider is the principle of aerodynamics. Aerodynamics. Aerodynamics is the study of the properties of moving air and the interaction between the air and solid bodies moving through it. It's a crucial field in engineering, particularly in the design of vehicles like airplanes, cars, and even bicycles. So aerodynamics is the study of the movement of air and interaction of the moving air and solid bodies. So it applies in vehicles, in aircrafts, and even in bicycles. So I'm going to be considering some key concepts. The first is lift. Lift. The force of lift is the force that directly opposes the weight of an aircraft and holds the aircraft in the air. An aircraft is moving through the air, there is a lift force that is generated. So it's a lift that opposes the weight of an aircraft and keeps the aircraft in the air. Next is drag. Drag is the resistance force caused by the motion of a body through a fluid such as air. So drag, the opposite of drag is thrust. Thrust is the force that propels a body forward. So I've mentioned four now. The first is lift and weight. Those are the opposite forces. Lift keeps the aircraft up, while weight, due to the weight of the aircraft, is bringing the aircraft down. And then we have drag and thrust. So drag is a force that is resistance force caused by the motion of the aircraft through the air. So how well the aircraft moves through the air depends on these four forces, and also it depends on how streamlined the body of the aircraft is. So that's what I'm considering under aerodynamics. And then we also have the flow patterns, the ways in which air moves around an object, including laminar flow, which is smooth, and turbulent flow, which is chaotic. Flow patterns are also a crucial part of aerodynamics. Aerodynamics plays a significant role in improving the efficiency and performance of vehicles by minimizing drag and optimizing lift. The aim of it all is to minimize drag by streamlining the aircraft body and optimizing lift. That is what we desire, so that we can have optimum efficiency and performance. It's also crucial in sports engineering, where the design of equipment like golf balls and racing vehicles can significantly impact performance. It's not only in aircraft that aerodynamics apply, even in sports engineering, in racing. If you observe the vehicles used for racing, they are not the normal type of vehicles that we have. They are extremely streamlined to reduce the drag. Also in bicycles, racing bicycles, if you notice the posture of the riders, they tend to put their head down so that they can just reduce drag to the minimum. The second is the engines, the aircraft engines. Aircraft engines are complex machines designed to generate the thrust necessary for flight. They come in several types, each with unique characteristics and uses. So aircraft engines, they are very important for the operation of the aircraft, and they are extremely complex machines designed to generate the thrust necessary for flight. The turbofan engines. The structure: these engines have a large fan at the front, followed by a series of compressors, combustion chambers, turbines, and exhaust. That's the structure. As you can see in the diagram, they have a large set of fans at the front, followed by a series of compressors, combustion chambers, turbines, and exhaust. The use is commonly used in commercial jetliners due to their high efficiency at high speed and altitude. Advantage: they are very quiet and more fuel efficient compared to other types. That is it for the turbofan engines. The turboprop engines. The structure: a turbine engine connected to a propeller. Turboprop, there's a turbine engine and there's a propeller in front. The use is ideal for short to medium haul flights and slower speeds, such as in regional airliners and cargo planes. It's more efficient at lower speeds and at shorter distances. In short, turboprop, there's a big propeller in front and there's a turbine engine connected to it. So it's ideal for medium, short to medium off flight and for slower speeds. The turbojet engines. The structure is similar to that of turbofans, but without the large fan at the front. It's primarily used in military aircraft and older commercial aircraft. It's very capable at high speeds. So this is the third I'm considering. I consider the turbofan, the turboprop, and now the turbojet engine. Piston engines. Piston engines. The structure. Internal combustion engines similar to those used in cars but specifically designed for aviation. It's common in smaller general aviation aircraft. The advantage is simpler and less expensive than turbine engines. Yes, some aircrafts, though very small, still use piston engines. The piston engines is what automobiles use. So there's, it could be 4 pistons, could be 8. So there are pistons, that convert, these engines convert the up and down movement of the pistons into reciprocating motion of the crankshaft to generate power. Whereas in the turbine engines, there's nothing like that. There are no pistons, but there are a set of compressors, a set of turbines that rotate and convert and generate power. For the turboprop engines, the power is directed to rotating the propeller, while for the turbojet engine and turbofan engines, a large amount of power is and a large amount of the thrust is generated through the exhaust. Yes, we also have ramjet and scramjet engines. Ramjet and scramjet engines. Structure engines that have no moving parts and compress air using the aircraft speed. These engines, they don't have moving parts in terms of pistons and the likes, but then they convert the speed, they use the speed of the aircraft to compress air and generate thrust. They are used in high-speed military and experimental aircraft. They are very efficient at high speeds. That's the advantage they have. And yes, we also have the electric engines. What's their structure? They are powered by electric motors using battery or hybrid systems. They are emerging technology for small aircraft and urban air mobility solutions. The advantage, potential for reduced emissions and noise. So these engines, electric engines, they are powered by electric motors using batteries or hybrid systems of battery and some other sort of power system. They are used in small aircraft and urban air mobility solution, and because of the fact that they are electric engines, reduced emissions and noise. Aircraft engines are meticulously designed and tested to ensure they provide reliable performance under a wide range of conditions, including extreme temperatures and altitudes. They are meticulously designed and tested to ensure that they provide a reliable performance under a wide range of conditions. I said they are complex engines. There is a series of sensors placed at different parts of the engines to monitor different things, such as vibration, such as heat. And aircraft engines are built to work and operate well in extreme conditions, extreme temperatures of heat and cold, and also at very high altitudes. Number 3, the flight control surfaces. Flight control surfaces are critical components on an aircraft that allow pilots to control its altitude and direction. These surfaces are typically divided into primary and secondary controls. So you might wonder, how do we control the movement of an aircraft? For vehicles we have the steering, and then we have the tires, we have the wheel. But in aircraft, aircraft do have landing gear, but that's for ground operations. How do we maneuver the aircraft in the air? That's why we have flight control surfaces. So they are divided into 2 primary control surfaces and secondary control surfaces. Primary flight control surfaces. We have first the ailerons. The location, they are located on the trailing edge of each wing, usually near the wing tips. And what's the function? Control roll about the aircraft's longitudinal axis. When the pilot moves the control sticker or yoke to the left or right, one aileron moves up while the other moves down, causing the aircraft to roll in the desired direction. Okay, so this is used to control the roll of an aircraft. And the roll is about the longitudinal axis. So when one goes up, the other one goes down, thus controlling the roll of the aircraft. The next is the elevators. Location on the trailing edge of the horizontal stabilizer at the tail of the aircraft. The elevators is located at the trailing edge of the horizontal stabilizer at the tail of the aircraft, and what the function is used to control pitch about the lateral axis. The pitch, the up and down movement. uh, by moving the control stick or yoke forward or backward, it causes the elevator to move up and or down, pitching the aircraft nose down or up respectively. So this is used to control the up and down movement about the lateral axis, about the aircraft's lateral axis. Next is the rudder. It's located on the trailing edge of the vertical stabilizer, also known as the fin. The function is that it controls yaw about the vertical axis. The rudder pedals allow the pilot to move the rudder left or right, yawing the aircraft nose in the corresponding direction. This is used to control the left or right movement, the yaw of the aircraft, and yaw is about the vertical axis. So I've talked about three motions now on the aircraft. I've talked about the motion about the vertical axis, the yaw, motion about the lateral axis, and the motion about the longitudinal axis. So next now, I'm going to be considering the secondary flight control surfaces. The secondary flight control surfaces. Number one, I have the flaps. The location of the flaps is on the trailing edge of the wings, closer to the fuselage than the ailerons. The function is to increase lift and drag. Increase the lift and drag, allowing the aircraft to fly at slower speeds, which is particularly useful during takeoff and landing. Flaps can be extended to various positions. So we have the flaps. It's used to increase lift during takeoff and increase drag during landing, allowing the aircraft to fly at slower speeds. So it is very useful at takeoff and landing respectively. So flaps can be extended to various positions on the aircraft, but it's typically on the trailing edge of the wings closer to the fuselage than the ailerons. Next is the slats. It's located on the leading edge of the wings. The function is to increase lift by changing the wing shape and improving airflow at low speeds, typically during during takeoff and landing. So slats, they are located on the leading edge of the wings, and it increases lift by changing the wing shape and improving airflows at low speeds. It's typically useful during takeoff and landing. I also have here the spoilers. The spoilers on the upper surface of the wings. The function is to reduce lift and increase drag. They can be used to assist in descent, slow down after landing, and aid in roll control by operating asymmetrically. Spoilers, they are located on the upper surface of the wings. The function is to reduce the lift and increase drag. So they can be used to assist in descent, and this is when the aircraft is about to land. So reducing lift and increasing drag will then be useful. So if you know the way they operate, when the aircraft is about to descend, the upper surface of the wing, there's a portion that will just lift up. And increase drag by doing so. And also in roll control by operating asymmetrically. The next secondary flight control surface that I will be considering is the trim tabs. The location, there are small adjustable surfaces attached to the trailing edge of the primary control surfaces, such as ailerons, elevators, and the rudder. The function is to reduce the pilot's workload by maintaining a steady flight attitude without continuous control input. To reduce the pilot's workload by maintaining a steady flight attitude, whether the aircraft is on a cruise or is accelerating, ascending or descending, to maintain a steady flight attitude without continuous control input. So trim tabs, they are small surfaces. They are usually attached to the primary control surface, the three that I've mentioned earlier, and at the trailing edge of them. So they also help the pilot, so that the pilot does not have to just be controlling as he's controlling the yaw, controlling the roll, controlling the pitch. No, the trim tabs helps to keep a steady flight attitude. As I wrap up this, know that each of these control surfaces plays a vital role in the safe and efficient operation of an aircraft, enabling precise control over its flight path and stability. As I said earlier, there are no wheels, there are no steering, there are no tires, no in the air. But these control surfaces, by a careful combination and mastery of these surfaces, we can precisely maneuver the aircraft in the air, and also they help in maintaining in keeping an aircraft in its flight path and stability. So each of these surfaces have a vital role, especially the primary ones, in the safe and efficient operation of an aircraft. Number 4, stability and control systems. Stability and control systems. Stability and control systems in aircraft are crucial for ensuring smooth, predictable, and safe flight. These systems manage the aircraft's orientation, speed, and response to external forces. Stability and control systems. So that's the next I'm going to be considering. Let's dive into both stability and control aspects. Stability. First, we have static stability. Okay, under this, we have positive static stability. That is, if an aircraft returns to its original position after a disturbance, it is considered to have positive static stability. Neutral static stability. If an aircraft remains in its new position after a disturbance, it has neutral static stability. And then negative static stability. If an aircraft continues to move away from its original position after a disturbance, it's said to have a negative static stability. So the first I'm doing is that I want to consider this concept of stability, static stability as the first. We have the positive, we have the neutral, we have the negative static stability as I have explained. If an aircraft returns to its original position after a disturbance, is considered to have positive static stability. If it remains in the new position, it's neutral. But then if it continues to move away, further and further away from the original position after a disturbance, then it has a negative static stability. Next is the dynamic stability. As it is with static, we also have 3 types of dynamic stability here: the positive, the neutral, and the negative. Then positive dynamic stability, over time, the oscillations caused by a disturbance decrease and the aircraft returns to its original state. Neutral, the oscillations remain constant over time, and then negative, the oscillations increase over time, leading to instability. Similar to what I just said for the static. And then for the control systems, mechanical control systems, these are cables, pulleys, rods, and other mechanical linkages to connect the pilot's controls to the control surfaces. They are common in smaller or older aircraft. I just talked about the control surfaces. How are they controlled? Are they mechanically operated? Are they hydraulically operated? Are they electrically or electromechanically operated? How are they operated? That's what I'm going to be considering. So the first is the mechanical control systems. When we use cables, pulleys, or a collection of pulleys and rods or other mechanical linkages to connect the pilot controls, and this from the pilot seat to connect the pilot control to the control surfaces, either the ailerons, either the rudder, either the elevator, the control surfaces, then we are said to be using mechanical control systems. Now this type of control system is common in smaller or older aircraft. Newer aircraft use something different. Next is the hydraulic control systems. That is the use of hydraulic fluid under pressure to move the aircraft's control surfaces. This provides greater force and reliability, and it is common in larger and modern aircraft. Hydraulic control systems. By the time we use fluid, pressurized fluid, to control these surfaces. So I don't know what the fluid could be, but it is the aviation fluid. The aviation fluid. The fluid used in aviation, not just different from transmission oil used in vehicles, but it works similarly to that. So hydraulic control, they provide greater force and reliability, and they are common in larger and modern aircraft. And then fly-by-wire systems. The use of electronic signals to control actuators that move the control surfaces. The use of electronic signals to control actuators that move the control surfaces. They offer reduced weight, increased reliability, and advanced control features. They often include redundancy and sophisticated software for improved safety. Fly-by-wire systems. At the time you use electronic signals to control actuators, this is more like electromechanical controls. The use of electronic signals to control actuators that move the control surfaces. Because there are no mechanical linkages, here, they offer reduced weight and increased reliability, and as well as advanced control features. They reduce redundancy and sophisticated software. So they include redundancy and sophisticated software for improved safety. Next, I have enhancements and stability augmentation. Enhancements and stability augmentations. That is, enhancement and what we augment the stability of an aircraft. The yaw damper, the autopilot. First, yaw damper. Yaw damper reduces yaw oscillations, dodge roll, by automatically applying rudder corrections. Automatically applying rudder connections. It's not everything that the pilots may be doing. The workload will be too much. That's why we have enhancements and stability augmentations. The yaw damper reduces yaw oscillation, known as dot roll, by automatically applying rudder corrections. Next is the autopilot. Autopilot, this is very important. The use of automated system that can control the aircraft flight path, altitude, and speed. It reduces pilot workload, especially during long flights or adverse weather conditions. During long flights, I know there will be a stage in flight where the plane will be, how should I put it now? Where the flight paths, will just be defined. In such a case, we can deploy the autopilot. It can control the aircraft flight path, altitude, and speed. And it also reduces pilot workload, especially during long flights or adverse weather conditions. There are some flights where the plane will be in there for long hours, 6-8 hours or even more. So autopilot can be deployed in such situations. FMS, the flight management systems. It integrates navigation, performance, and aircraft operations control into a single system. It optimizes flight efficiency and safety. We also have the SAS, the stability augmentation systems. It automatically makes more adjustments to the control surfaces to maintain stability, especially useful in helicopters and unstable fixed wing aircraft designs. So these are enhancement and stability augmentation means. The FMS, the SAS, the flight management systems, and stability augmentation systems, they all have the aim of enhancing controls. Design considerations. The center of gravity. Proper center of gravity placement is critical for stability and control. Forward center of gravity increases stability but decreases maneuverability. Aft center of gravity increases maneuverability but decreases stability. The center of gravity, as proper center of gravity placement is critical for stability and control. So you just have to take this into consideration when designing the aircraft and also when loading the aircraft. An aircraft can be designed with a good center of gravity placement, but when it's being loaded or when passengers are on board, the center of gravity could change. So all these have to be put in consideration for optimum stability and control. Next, under wing design, we have the dihedral angle, upward angle of the wings, which enhances roll stability. Sweep-back angle and wing placement affect lateral and directional stability. In short, we have many types of wing design. We have the anhedral, we have the dihedral, we have the different types of wing designs. So the choice of wing design will reflect on the stability and the control of the aircraft. Dihedral angle enhances roll stability. Sweep-back angle and wing placement affect uh, lateral and directional stability. By carefully balancing these elements, aircraft designers ensure that an aircraft is both stable and controllable, providing a safe and efficient flight experience. By carefully balancing these elements, all these elements that I've mentioned, designers can ensure that an aircraft is both stable and controllable, providing a safe and efficient flight experience. So that will be all that I'll talk about under stability and control systems of an aircraft. Number 5, navigation systems. Navigation systems. Aircraft navigation systems are essential for ensuring the safety and efficiency of flights. They encompass a variety of technologies and systems. Compared to vehicles and cars, where you can use your vision and your hearing, for navigation. I mean, you can literally see where you are going, and you also have the windscreen. You can hear the bonnets from coming vehicles. But when you are flying a plane, you need advanced navigation systems. And also, it's relatively easier to navigate when you are driving because you have buildings around, and it's easy to navigate and to get where you are going. But when you are flying a plane, everywhere looks almost the same. It's not easy at all to know the destination you are going by just your vision or by your hearing. So you need advanced navigation systems to make sure you are on flight, to ensure safety and efficiency of flight. So these navigation systems encompass a variety of technologies and systems which I am going to be mentioning. The first is inertial navigation system, the INS. How does this work? It uses accelerometers and gyroscopes to measure the aircraft's movement and orientation. It provides precise information on the aircraft's position, velocity, and attitude. Okay, the inertial navigation system, by combined use of accelerometers and gyroscopes, it measures the movement of the aircraft and the orientation. Now I said it's not possible to be using your eyes, vision, your eyes to be like physically looking at the surroundings to be moving the aircraft. No, it's not possible. That's why you have to make use of the INS, the use of accelerometers and gyroscopes to measure the aircraft's movement and orientation. It also provides precise information on the aircraft's position, velocity, and attitude. Especially when you are the pilot of a very big aircraft, the use of INS will provide precise information on the position, the velocity, and the attitude of the aircraft you are flying. Number 2, Global Positioning System, GPS. Alright, this is a satellite-based navigation system that provides real-time location and time information. It's often integrated with other systems to enhance accuracy and reliability. Aircraft also make use of GPS. So it's a satellite-based navigation system that provides real-time location and time information to know the exact location. Where are you flying? Are you still on course? Are you still on your flight path, or you've deviated? And the GPS on the aircraft is integrated with other systems to enhance accuracy and reliability. These information are very, very crucial when flying an aircraft for safety and for efficiency. Flight Management System, the FMS, a central computer system that manages flight plan data, navigation, and guidance. It interfaces with other systems to automate various flight operations such as route planning and fuel management. What's the flight management system? That's what I just talked about. So it uses computer to manage the flight plan data, navigation, and guidance. As with the GPS, it also relates with other systems to automate various flight operations such as route planning and fuel management. Route planning. Where are you coming from? What's the destination? What is the efficient and the most optimum route to pass? How about the weather conditions? Which the flight route that you're about to take? How is the weather condition? How is the atmospheric conditions there? These are the factors that we have to consider to determine the optimum route, and also fuel management. How much fuel must you carry on board? These information are very important for safety and for efficiency, and that's exactly what the flight management system does. Next is the radio navigation systems. The radio navigation systems. I have here the VOR, that's the VHF, very high frequency omnidirectional range. What does it do? It provides azimuthal information to aircraft, helping pilots determine their direction relative to a ground station. Next, the DME, distance measuring equipment. It measures the slant range distance between the aircraft and a ground station. And then the ILS, instrument landing system. It assists in landing by providing horizontal and vertical guidance. Assists in landing by providing horizontal and vertical guidance. So I'll talk about these three. They are radio navigation systems, the VOR, the DME, and the ILS. Number 5, the automatic dependent surveillance broadcast. ADSB, automatic dependent surveillance broadcast. It transmits the aircraft position, velocity, and other data to air traffic control and other aircraft. It enhances situational awareness and safety. Okay, so this transmits the data about the aircraft, such as position, velocity, and other important data to an aircraft's traffic control and other aircraft. This helps in monitoring the aircraft. It increases situational awareness and safety. Next is the tactical air navigation. TACAN, TACAN. The tactical air navigation. What's its function? It is used primarily by military aircraft for navigation. It provides bearing and distance information. So the tactical air navigation is used majorly by the military aircraft, and as with others that I've been talking about is for navigation. It provides bearing and distance information about the aircraft. In military, for military aircraft, navigation is very, very important. That's why some of these additional systems are there, which normally may not be in the commercial aircraft. The Ground Proximity Warning System, GPWS. What does it do? It alerts pilots if the aircraft is in immediate danger of flying into the ground or an obstacle. It uses inputs from various sensors to determine the aircraft's altitude and proximity to terrain. I mentioned earlier that there are many sensors on the engines, not only the engines, on the airframe and various parts of the aircraft. There are various types of sensors there. So this particular system, the Ground Proximity Warning System, it allows the pilots if the aircraft is in immediate danger of flying into the ground or an obstacle, if there is a solid body that is approaching the aircraft, or whether the aircraft is approaching a solid body such as the ground. It uses inputs from various sensors. This is how it works, using inputs from various sensors to determine the aircraft's altitude and proximity to terrain. This ensures that the aircraft does not crash. The Ground Proximity Warning System. Traffic Collision Avoidance System. Traffic Collision Avoidance System. Okay, this monitors the airspace around the aircraft for other transporter equipped aircraft. It provides resolution advisories to avoid mid-air collisions. So this system is simply put in place for collision avoidance. And how does it do this? By monitoring the airspace, the space around the aircraft, for other transporter equipped aircraft, in order to detect if other aircraft or other aerial vehicles are approaching. It also provides resolution advisories to avoid mid-air collision. That's it for the Traffic Collision Avoidance System, TCAS. Number 6, aircraft systems. Aircraft systems are integral to the operation, safety, and performance of an aircraft. Here is an overview of the key systems found in most modern aircraft. So I've talked about the navigation, controls, the engine, and some other things. Now I want to talk about the aircraft systems. They are integral to the operation, safety, and performance of an aircraft, and I will be considering some key systems found in most modern aircrafts. The first is the power plant, the engines. I've talked about this before. Jet engines used in commercial and military aircraft for high-speed flight. The turboprop engines, it combines jet and propeller technology commonly used in regional and cargo aircraft, and also the piston engines typically found in smaller general aviation aircraft. Alright, next now the electrical system. Okay, I have not talked about this before. First, power generation. It includes generators or alternators powered by the engines. Yes, as the engines, it's not all the power generated by the engines that is being used for thrust or being used to drive the propeller, as the case may be. There's some portion of the power generated can be used to power either generators or alternators used for other electrical systems in the aircraft. Distribution ensures power is delivered to all necessary components, including avionics, lighting, and environmental systems. As power is generated, it has to be appropriately distributed. Avionics, that's the electrical part, the lighting, lighting of the cabin, lighting of various parts in the aircraft, and also environmental systems. I talked about sensors, I talked about actuators earlier. So some of these things need electricity to be powered. And backup systems, batteries and auxiliary power units (APUs) provide power if the main systems fail. Okay, so in case some of these power supply systems that I've talked about, in case they fail, there are also backup systems such as batteries and the APU to provide power if the main systems fail. Number 3, hydraulic system. I talked about this briefly before when I was talking about flight control surfaces, and some of them I said some of them are mechanically operated, some hydraulically operated. So hydraulic system powers critical components. Now it's not only the flight control surfaces, it can also power the landing gear, brakes, and of course flight control surfaces. Hydraulic system uses hydraulic fluid pressurized by pump connected to the engines. Hydraulic fluid pressurized by pumps connected to the engines. So hydraulic systems are also very important in the aircraft. They are used for many things in the aircraft. Pneumatic system. It provides air for environmental control systems, de-icing and pressurization. It's often sourced from engine bleed air. The pneumatic system, this uses highly pressurized air. So it's often gotten from the engine. Bleed air simply means compressed air, highly compressed air, air that is taken, that is drawn from the compressor stage of the turbine. Highly pressurized air. So the pneumatic system provides air for environmental control systems. Yes, bleed air can also be used for de-icing. De-icing simply means when some parts, especially the tips of the aircraft, are getting, because of the temperatures and because of the speed of light, ice starts to form on the leading edges, either of the wings or some other part like that. So there may be need for de-icing. So pneumatic system, bleed air can be used for such things. Next, the fuel system. Manages fuel storage and delivery to the engine. Includes fuel tanks, pumps, valves, and fuel management systems. Okay, fuel system. So this ensures that fuel is delivered to the engine in the right proportion. It also manages fuel storage. There are some aircraft that makes use of external tanks. Some fuel can be stored, some part of the fuselage, some in the wings. So fuel system manages fuel storage and delivery to the engines. It may include fuel tanks, pumps, valves, and fuel management systems. Next is the avionics system. This includes communication systems, navigation systems, flight management system, and the autopilot. First, the communication systems. VHF, UHF radios for communication with air traffic control. Navigation systems, the use of GPS, INS, VOR, ILS, and more for precise navigation. I mentioned some of these things before. Flight management system, it integrates navigation, performance, and guidance function and the autopilot, which automatically controls the aircraft's flight path. So avionics, so this simply involves these things that I talked about: communication, navigation, the autopilot, and the flight management systems. So to ensure optimum safety and efficiency in aircraft performance. Environmental Control System, ECS. What does it do? It maintains cabin pressure, temperature, and air quality. It also includes air conditioning, pressurization, and anti-icing systems. So this environmental control system, it monitors and maintains the cabin conditions such as pressure, temperature, and air quality. So it does this by pressurization, air conditioning, and anti-icing systems. That's what the environmental control system does. Okay, moving on, number 8, the landing gear system. The landing gear system, it consists of wheels, struts, brakes, and steering systems. The landing gear is very important for ground maneuvers. In the air, we can have flight control systems such as the ailerons, the taps, and the elevators, the rudder, and others that I've talked about. But on ground, we need the wheels. We need the wheels to maneuver the system, because no, the reason flight control system work is because when the aircraft is in the air, is flying, and then no air is moving against it. Because of that, the flight control surfaces can make use of principle of aerodynamics and all that to maneuver the aircraft. But while on ground, we need the traction between the wheels and the ground for maneuvers. So landing gear code can also include retractable systems to reduce drag during flight. Yeah, there are some, in fact, most of uh, the commercial aircraft that we have retractable landing gear. That is, after takeoff, the landing gear will go back inside, and during landing, the landing gear can then be brought out again. Though there are still a few, very few, especially the smaller aircraft, that have fixed landing gear systems. And also there are different type of landing gear. Perhaps I will talk about that later. We have the tricycle landing gear. We have for aircraft that land on we have skis for aircraft that land on snows, and different type of landing gear systems. Number 9, the flight control system. I've talked about this before. Primary controls and secondary controls. For the primary controls, you have the ailerons, the elevators, and rudder for basic maneuvering. And for the secondary controls, the use of flaps, slats, and spoilers for enhanced control during takeoff, landing, and cruise. So the flight control systems, primary and secondary control systems, I've talked about this before. Ice protection system. This is to prevent ice accumulation on critical surfaces like wings, engines, and sensors, and use of thermal or heating mechanical pneumatic boot method. Now, why do we need to prevent ice formation? It's very important because it can disturb the aerodynamics of the aircraft, and ice can accumulate on wing tips and on some other parts of the aircraft. So it's necessary to prevent ice accumulation on critical surfaces like wings, like engines, and sensors. Sensors are very important to get feedbacks from various parts of the aircraft and ensure optimal function of those parts. So we can use thermal or mechanical methods to prevent ice formation. Heating methods can be put in such strategic places that ice are likely to form, and also the use of mechanical pneumatic such as bleed air to blow away ice that form away. So use of thermal heating or mechanical pneumatic boots method to prevent ice formation. Fire protection system. This detects and extinguishes fire in engines, cargo holds, and other critical areas. It includes fire detection sensors and extinguishing agents. Now, detects and extinguishes fire in engines, cargo holds, and other critical areas. This is very important. Take for instance, an aircraft is flying at a very high altitude and is a fire outbreak, No, that would be very dangerous. That would be very deadly. So it's necessary to have fire detector sensors and extinguishing agents in various parts of the aircraft, the cargo holds and other critical areas to prevent disaster and the airplane from crashing. Number 12 under aircraft systems is the emergency systems. Emergency locator transmitter (ELT), which sends a distress signal in the event of a crash. We also have the life support systems such as oxygen masks and life rafts for passenger safety. So emergency systems. In the case of a crash, in the event of a crash, so the emergency locator transmitter will send a distress signal, perhaps to the nearby station, to the nearby depot. We also have so that such aircraft station can send support and a rescue team to come look for the airplane that has crashed. There are also life support systems on board the aircraft, such as oxygen masks and life rafts for passenger safety. Say the aircraft crashes into an ocean, so there should be oxygen masks and life rafts for passenger safety. Moving on to the next, we have the landing gear. The landing gear is a crucial component of an aircraft which is responsible for supporting the aircraft during takeoff, landing, and while it is on ground. Here is a detailed look at the landing gear system. So like I said, landing gear is very important. Flight control surfaces will only work when the airplane is in air, but while it's on ground, it's the landing gear that will be used for all ground maneuvers. So landing gear is also useful during takeoff and landing and for ground operations on the aircraft. First, the tricycle landing gear. It has a nose wheel and then main gears. So the nose gear, one wheel or set of wheels located at the front of the aircraft, and then main gears, two sets of wheels located near the middle of the aircraft. So this type of configuration is common for modern aircraft. So the way it works, it's like a tricycle. There's a wheel in front and then there are two wheels at the back. So the wheel in front, it can just be a wheel or a set of wheels, and at the back two set of wheels differently at the rear of the near the middle of the aircraft. That's it for the tricycle landing gear. For the tail wheel landing gear, the conventional landing gear, there's a small wheel at the rear of the aircraft. That's the tail wheel, and then the main gear, two sets of wheels located near the front of the aircraft. So it's common in old aircraft and some specialized aircraft. There are two wheels in front and one wheel at the back. That is our configuration for the tail wheel. It's not common these days again. Uh, it's only in older aircrafts that you can find such type of configuration. The third, fixed landing gear. The landing gear is permanently extended and does not retract. So this is common for simpler and lighter. This is simpler and lighter to build, to construct, as it does not involve any form of retraction mechanism, but it creates more drag. Because it does not make the body of the aircraft to be streamlined. The landing gear is permanently extended and does not retract. Retractable landing gear. So this is the opposite of what I just talked about, or the fixed landing gear. Here, the landing gear can be retracted into the aircraft during flight. Yeah, when the aircraft is flying, then depending on the type of retraction mechanism that is used, but commonly either mechanically used or hydraulically powered, but whatever means, the landing gear is retracted, is taken back into the aircraft. What does this lead to? It leads to reduced drag and also improves fuel efficiency and improves the speed of the aircraft. Now, what are the components of the landing gear? What can we find on the landing gear? Number one is the struts. And the struts is what absorbs the impact during landing. It absorbs the impact, and it's typically filled with hydraulic fluid and nitrogen gas to provide cushioning. The strut is what will absorb the impact of landing. The aircraft is coming from though when it's approaching landing, it will have already started slowing down, but the aircraft is still the weight is still a lot, so the strut is needed as it is what will absorb the impact during landing. So it's filled with hydraulic fluid and nitrogen gas to provide cushioning. Number two, wheels and tires. It's designed to handle high loads during landing and takeoff, and then it's often equipped with heat resistant properties to withstand friction and heat. Talking about the components of landing gear, wheels and tires. Now this depends on where the aircraft is going to land on. It could be wheels and tires if it's on land, it could be skis if it's on snows, it could be like float type of materials if it's on water, or it could vary. But if it's on land, we have wheels and tires designed to handle high loads during landing and takeoff, and is often equipped with heat resistant properties, heat resistant materials to withstand friction and heat. Number three, we have brakes. Brakes are located on the main landing gear wheels. On the main landing gear wheels. In the case of a tricycle landing gear system, that's in front. So it uses hydraulic or pneumatic system to slow down the aircraft during landing and abort. It uses hydraulic or pneumatic systems to slow down the aircraft during landing and abort. Okay, an aircraft is about to land, and there's we want to reduce the landing distance, so you just have to apply the brakes so that it will land quickly. And let's say there's an abort, an aircraft is about to fly, but then something happens, you just have to stop the flight. No, brakes are still needed. So it's located on the main landing gear wheels. Next, the steering system. The number 4 component is a steering system. This provides directional control while taxiing. Taxiing simply refers to grand maneuvers. So an aircraft in the depot want to tow it to a place, take it to another place. So we have the steering system there. So it's typically controlled through a tiller or rudder pedals. That's it for the steering system or the landing gear. Operation of the landing gear. Extension and retraction. I've been mentioning this already. Extension and retraction. It could be through hydraulic systems, electric systems, or manual systems. For hydraulic systems, the use of hydraulic power to extend and retract the landing gear. For electric systems, some smaller aircraft may use electric motors for landing gear operation. While the manual systems is rare, but some aircraft have a manual crank for emergency situations. These are the 3 systems that are used for extension and retraction. Then locking mechanism. That's number 2. It ensures the landing gear stays in the extension or retracted position. It ensures the landing gear, when it's extended, stays there, or when it's retracted, it stays there. And then mechanical locks engage automatically. So landing gear usually have locking mechanism used for these purposes to ensure the landing gear stays either in the extended or in the retracted position. Next, I'm going to talk about the safety features. Number 1, gear position indicators. It provides visual confirmation of the landing gear status, either extended or retracted or in transit. So safety features, gear position indicators. It will tell us, give us a confirmation what's the status of the landing gear. Has it been fully extended or fully retracted, or is in transit? Is in either in the two, in between the two. So the gear position indicator is what will let us know that. Next, the warning systems. It alerts the pilot if the landing gear is not in the correct position for landing. This could be very dangerous. I already said the landing gear have strut which bears the impact of landing. Let's say for instance the landing gear has not been fully extended, and then the aircraft land. That can cause a lot of damage. The landing gear system and even the fuselage the body of the aircraft can hit the ground, which could be dangerous. So we have warning systems which will alert the pilot if the landing gear is not in the correct position for landing. Number 3 safety feature is the emergency extension systems. The emergency extension systems. This allows the pilot to manually extend the landing gear if the premise system fails. I talk about the electric, hydraulic, and the manual. So it allows the pilot to manually extend the landing gear if the premise system fails. It can be mechanical, hydraulic, or gravity-based systems. Mechanical, hydraulic, or gravity-based systems. That is for the emergency extension systems. Next is the anti-skid prevention. The anti-skid prevention. It prevents the wheels from locking up during braking. It prevents the wheels from locking up during braking. So while brakes are being applied, the wheels can still rotate and then gradually slow down the vehicle, the aircraft I mean. So it also ensures optimal braking performance and reduces tire wear. The anti-skid system has these two functions: to prevent the wheels from locking up during braking and to ensure optimal braking performance and to reduce tire wear. As I approach the end, the maintenance of landing gear. Maintenance of landing gear. The first maintenance is regular inspections. Regular inspections. Visual inspections for wear, corrosion, and damage. Parts of the aircraft of the landing gear should be visually inspected for wear, corrosion, or for damage, and also functional checks to ensure proper operation. Functional checks to ensure proper operation of the landing gear. Number 2 maintenance that can be done on the landing gear is tire replacement. Regularly replace tires due to wear and tear, because tires are critical for safe landing and takeoff. So there's no need to, when the tire is not at the optimal condition, the best is just to replace it because of the overall safety of the aircraft. We should not compromise safety of passengers and aircraft because of our inability or unwillingness to replace tires as at when due. Tires should be regularly replaced due to wear and tear. Number 3 brake maintenance. Brake maintenance. Regular checks and replacements of brake pads and discs. And then this is to ensure effective braking performance. As it is with tires, so it is with the brake. It should be regularly checked and replaced when due, the brake pads and the discs. So this is for effective, efficient, optimum braking performance of the landing gear of the aircraft. Number 4, we have here the hydraulic system maintenance. Hydraulic system maintenance. Regular checks for leaks and hydraulic fluid levels. It ensures the reliability of the extension and the traction system. The hydraulic system should be checked regularly. All the connections and everything should be checked. Check for leaks and also check for the hydraulic fluid levels. The fluid level should be topped up when necessary so that the hydraulic system can be in optimal condition. This is to ensure the reliability of the extension and retraction system. Number 8, safety systems. Safety systems. Aircraft safety systems are designed to protect passengers, crew, and the aircraft itself. There are a lot of safety systems which I'm going to be considering here, and the overall function is to protect passengers, the crew, and the aircraft itself. So here is an overview of the primary safety systems in modern aircraft. Overview of the primary safety systems in modern aircraft. Fire protection system. Fire protection system. Detection, suppression, and engaging fire bottles. The first, detection. Sensors are located in engines, I mentioned it before, cargo loads, and other critical areas to detect smoke or fire. Sensors are located in the engines, in cargo loads, and other critical areas to detect if there's a smoke or if there's fire. Suppression. Fire extinguishers with halons or other agents automatically or manually deploy to extinguish fire. There are fire extinguishers also. and then engine fire bottle, specific extinguishers for engine fires activated by the pilot. So this is the first safety mechanism there, the fire protection system. Emergency locator transmitter, ELT. It transmits a distress signal with the aircraft location in the event of a crash. In the event of a crash, I believe I mentioned this before. It also helps search and rescue teams locate the aircraft quickly. The emergency locator transmitter, it transmits a distress signal when the aircraft position with the aircraft position in the event of a crash. It also helps in search and rescue teams to locate the aircraft quickly. Oxygen systems, that's number 3. Passenger oxygen masks deploy automatically if the cabin pressure drops, and then the crew oxygen systems provides oxygen masks for pilots and cabin crew, and portable oxygen bottles available for medical emergencies. So there should be oxygen systems also in the aircraft as part of the safety system, both for the passenger if the cabin pressure drops. When an aircraft is flying at high altitudes, very high altitudes, the pressure there is not the same pressure as we have normally at. It's different from the sea level pressure. So if the pressure drops, there should be oxygen masks that passengers can use also for the crew, and there should be portable oxygen bottles available for medical emergencies. Evacuation systems. Number 4 safety system, that's the evacuation systems. Number 1, it should include emergency exits and slides. Doors and overwing exits equipped with inflatable slides for rapid evacuation. There should be rafts and life vests provided for water landings. And then there should be all lighting illuminate paths to exit during low visibility conditions. So evacuation systems include emergency exits. Let's say there's a fire outbreak in the cabin, there should be emergency exits and slides. Also, for a crash landing in the water, there should be a raft and life vests, for passengers, and there should be floor lighting to illuminate paths to exit during low visibility conditions. Ground proximity warning systems. I've mentioned this before, so I think GPWS, it alerts pilots if the aircraft is in immediate danger of flying into the ground or an obstacle. It alerts pilots if the aircraft is in immediate danger of flying into the ground or an obstacle. Enhanced terrain awareness and warning systems for advanced terrain mapping. The ground proximity warning systems has 2 functions. The first, to alert pilot if the aircraft is in immediate danger of flying into the ground or a solid body, an obstacle. It enhanced by terrain awareness and warning systems for advanced terrain mapping. So it has 1 function and is enhanced by what I just mentioned. Next is the traffic collision avoidance system. It monitors the airspace around the aircraft for other transporter equipped aircraft. It provides advisories and instructions to avoid mid-air collisions. Traffic collision avoidance system. I've mentioned something like this before too. It monitors the airspace, the space around the aircraft for other transporter equipped aircraft. Next is the autopilot and the autothrottle systems. It reduces pilot workload and enhances flight precision. It automatically manages flight path and engine thrust. Now this is very useful in cruise, when the aircraft is in a cruise, because there's nothing much to do. So it reduces pilot workload and enhances flight precision. It automatically manages flight path and engine thrust. I have also the fly-by-wire systems. It replaces traditional manual controls with electronic interfaces. It improves response time and accuracy of control surfaces. Fly-by-wire systems. It replaces traditional manual controls with electronic interfaces. It also improves response time and accuracy of control surfaces. Number 9, the 9th safety system in the aircraft is the structural monitoring systems. The sensors monitor the integrity of the aircraft structure and also detect fatigue, stress, and potential failure points. structural monitoring system. This has to do more with the airframe, the body of the aircraft. So it monitors the integrity of the aircraft structure. You know, when an aircraft has been used for a long period of time, there could be fatigue, stress, and perhaps even cracks in the body, in the airframe. So the structural monitoring system senses, you know, these things, detects fatigue, stress, and potential failure points, as well as monitors the integrity of the aircraft structure. Okay, this is the last concept that I'll be talking about, and that's the phases of flight. The phases of flight. Phases of flight refer to the different stages an aircraft goes through from the time it begins its journey on the ground until it reaches its destination. Here is a detailed breakdown of each process. Phase of flight, you know, from the takeoff to the when it's in the air, to cruise, and then to descent, and then to landing. So phase of flight talks about all that. I'll be giving a detailed the explanation and breakdown of each phase. Pre-flight, that's the first phase. It involves planning, inspection, and boarding. During the planning, flight plan preparation, including a route, fuel, weather analysis, and weight considerations. For the inspection, aircraft is checked for mechanical and structural integrity, and boarding, passengers and crew board the aircraft, cargo and baggage are loaded. So this is very, very important. Before an aircraft, you know, takes off, there has to be pre-flight, and that involves planning, inspection, and boarding. During the planning, what's the destination of the aircraft, what's the weather analysis, what's the route, what's the fuel, how much fuel will it require, and what are the weight considerations, how many passengers, how about the cargo and baggage, how about the center of gravity of the aircraft, and many such considerations, you know, have to be many such considerations will come to mind. Also, aircraft is inspected, is checked for mechanical and structural integrity. All these are the activities that go on in the pre-flight phase. Next, we have the taxi. The first here is pushback. Aircraft is pushed back from the gate by a tug. And then there's taxiing. Aircraft moves to the runway using its own power, guided by ground control. So the pushback, aircraft is pushed from the gate by a tug. Usually, I've been to a depot before. There is a towing vehicle, and there is a tug that is connected to the aircraft. Typically, the landing gear, there's a part in the landing gear that the tug is connected to, and then there will be a towing vehicle. So aircraft is pushed from the gate by a tug. And then there is taxi. Here, aircraft moves to the runway using its own power. There are landing gears, so it moves by its own power, guided by ground control. The third phase is the takeoff. There are a couple of things here. The first is lining up, thrust, then thrust application, acceleration, rotation, and lift up. The first, lining up, aircraft aligns with the runway center line. Then thrust application, engines are throttled up to take off power. Acceleration, aircraft accelerates down the runway. Rotation, pilot pulls back on the control column to lift the nose. Lift off, main wheels leave the ground and the aircraft becomes airborne. So these five things here are very, very important. The lining up, the thrust application, acceleration, rotation, and lift up. Number 4, initial climb. There are 3 things here also: gear retraction, speed and altitude management, and noise abatement procedures. The first, gear retraction. Landing gear is retracted. Then speed and altitude management. Aircraft climbs to a safe altitude and accelerates to initial climb speed. Noise abatement procedures. If applicable, aircraft follows procedures to minimize noise impact on surrounding areas. So this just describes the initial climb. Gears are retracted, that's if there's a retraction system there. And then speed and altitude management, the aircraft climbs up to a safe altitude and accelerates to initial climb speed. And then if applicable, there are noise abatement procedures to minimize noise impact on the surroundings. After the initial climb, there's a climb. That's number 5. This includes transition to climb, thrust reduction, and en route navigation. The first, transition to climb. Aircraft climbs to cruising altitude following air traffic control instructions. It climbs up to that altitude where it's going to then continue for a while following instructions from the air traffic control. And then there's a thrust reduction. Engines are set to climb power which is less than takeoff power. Takeoff, we have to defeat the weight of gravity, and a lot of passengers and cargo and baggages in the aircraft, so usually very heavy. But then once the takeoff phase is over, in cruising there will be enough lift to counter the weight of the aircraft. So engine power can be reduced a little, thrust can be reduced a little. And then we have en route navigation. Aircraft follows its planned route, adjusting course as needed. It follows its flight route, adjusting the course as needed. Next stage is the cruise stage. Here, this involves level flight, monitoring, and passenger service. In the level flight, aircraft maintains a constant altitude and speed. Monitoring. Systems are monitored for proper operation and adjustments are made for efficiency. Now I talk about the autopilot system the other time. So in the cruise, since aircraft is maintaining a constant altitude and speed and is already on its flight path, so autopilot systems can be deployed there, and other various monitoring systems for proper operation and adjustments are made for efficiency. Here we can also have passenger service, because during takeoff and landing, the passengers will have to be on seat belt and they may not be able to. The flight may be a bit rough, but at cruise the flight is a bit smooth, and then cabin crew can provide food, beverages, and other services for the passengers. After the cruise, then there's a descent. Initial descent, thrust reduction, and descent planning. For the initial descent, aircraft begins its descent from cruising altitude towards its destination. When the aircraft is approaching its destination, then it will begin to descend gradually from the cruising altitude towards the destination. Then there's a thrust reduction. Engines are throttled back to descent power. We have to slow down because we are approaching the destination already. So there's a thrust reduction. And also there's a descent planning. Pilots coordinate with air traffic control for descent, clearance, and approach planning. So the pilots flying the aircraft, we have to coordinate with air traffic control for descent, clearance, and approach planning. Number 8, the approach. We have the approach phase, configuration changes, speed, and altitude adjustment. For the approach phase, aircraft follows a predetermined approach path towards the airport. There is a predetermined approach path towards the airport. And then configuration changes. Flaps, slats, and landing gear are deployed to prepare for landing. Now I talk about spoilers, flaps, and slats, and stuff like that help to reduce the speed by increasing drag. So they are deployed to prepare for landing. We also have speed and altitude adjustment. Aircraft is slowed and altitude is adjusted for a safe approach. Speed and altitude are adjusted appropriately for a safe landing. And 9 is the landing. There's a final approach. Aircraft is aligned with the runway and stabilized for landing. There's a touchdown. Main wheels make contact with the runway, and there's reverse thrust and braking. Engines may reverse thrust and brakes are applied to decelerate the aircraft. 3 things are involved there: final approach, touchdown, and reverse thrust and braking. So as the aircraft is approaching, then the wheels will touch down, and also we have reverse thrust and braking. Reverse thrust and braking to slow down the aircraft, to decelerate the aircraft. Number 10, taxi to gate. The runway exit. Aircraft exits the runway and taxis to the gate. Number 2, post landing checks. Systems are checked and engines are powered down as necessary. Number 3, arrival at gate. Aircraft arrives at the gate and is secured. So this is the 10th stage here, the taxi to gate. We have the runway exit, post landing checks, and arrival at the gate. where the aircraft arrives at the gate and is secure. Now, we also have the post-flight shutdown, disembarkation, post-flight inspection, and data logging. The first, shutdown. Engines are shut down and systems are turned off. Disembarkation, passengers and crew all exit the aircraft. Number 3, post-flight inspection. Aircraft is inspected for any issues or maintenance needs. And number 4, data logging. Flight data is recorded and reviewed. So these 4 things are part of the post-flight and mark the post-flight stage. The shutdown, engines are shut down. Disembarkation, people get out of the aircraft. Post-flight inspection, aircrafts are inspected for issues or maintenance needs. And data logging, where flight data is recorded and reviewed. Each of these phases requires precise coordination and communication between the flight crew, air traffic control, and ground personnel to ensure safety and efficiency. It's not only the crew, it's not only the pilots that has work to do. The flight crew, air traffic control, and ground personnel all have to work together to ensure safety and efficiency of each of these phases. They require precise coordination and communication. So that will be the end of this video on operation principles of aircrafts. I believe you enjoyed it. Okay, thanks for watching. If you have specific interest or you need more details on any of these concepts, please do let me know in the comment box below. Thank you very much.